Hello and welcome to Section 6, where we'll talk about all the tools that astronomers use to study the universe. In this awesome picture here, we're looking at 3 cube satellites, or CubeSats, being launched off. And a cube satellite is just a experiment entirely contained in your single cube. These are very popular devices nowadays to have a contained experiment. So with that, let's go ahead and jump over to our questions. As always, we'll start off by checking if everyone's keeping up with their readings and the materials, and we'll ask a simple question. A prism is able to spread up white light into a spectrum of colors based on what property? Go ahead and pause, figure out your answer, and come back. That property is going to be refraction. In this video, we'll actually talk about reflection and refraction, how they're related to each other. Magnification will come up mostly in the context of telescopes for this course. Now, aberration is related to the apparent motion of an object. It's due to, say, living on Earth that's rotating and orbiting a star, orbiting the sun. Our goals for this section is to build up the different tools that we'll see in astronomy and how we combine different observations to better understand the universe. The main ones are going to be comparing our 2 types of telescopes, which actually can be broken down into a refractor and reflections. Right? And from there, we'll start building up the different types of detectors that we can use. How do you take a light source and convert that into something your computer can analyze? As always, talk about all the satellites. Every dot here represents something that we have launched into space. And then speaking of space, we'll talk about the different crafts, rovers, and a little bit about colliders. Right? What can we learn by particle colliders? There are 2 main properties of light that we're going to explore and exploit when using and building telescopes. And that's going to be the properties of reflection and refraction. Now, these are the simplest case pictures that we can show you of a light coming in, bouncing out. But let's go into a little bit more detail. If we're talking about reflections, what's happening is that we're talking about a ray coming in. It'll have some incident angle. In this picture, that angle is measured with respect to the mirror. Right? If this is the surface of the mirror, we're going to measure the angle, the incident angle, to respect to this red line here. So that's the incident angle. Let's go ahead and clear this up again. Clear, close. All right. So we have this incident ray coming in, right, with respect to this angle here that's conveniently called 0. And that ray is going to clearly reflect off of this shiny object, a mirror. And we'd say, look, this reflected ray, this outgoing angle, has to equal this incoming angle. The incident ray is equal to the reflected ray. And that's just a property of reflection. To see this reflection property in action, I'm going to take a nice simple mirror here and aim at it with a laser pointer. So it'll be a nice green laser pointer here. And I'm going to have an incident ray hit the mirror, reflect off, and we'll see that the reflected ray is at the same angle. Now, obviously, this is very difficult to see. So what I'm going to do is kill the lights. Right. Let the camera adjust. Try again. Right. Still can really only see the part of the beam that's hit the mirror. So what I'm going to do is take a little can of smoke and just add some particles to the air. Let it now you can really see that incident ray versus the reflected ray. Let's add a little bit of smoke here. Right, getting a lot of Mission Impossible vibes here. So here's my incident ray. It comes in, hits the reflective object, and bounces. It reflects off, going away at the same angle. Instead of talking about reflections, let's now talk about refractions. Right? And this is what happens when light transfers between mediums. So let's call this out now. Here you can see the incident ray in. And if you look diligently at this picture, you can see a little bit of a reflected ray. You can just barely make it out. But that's not what we want to focus on. We're going to talk about this refracted ray. So putting this all out there now. The beam of light comes in at some incident angle, there's always going to be a reflected ray. Right? Think about glass. When you're trying to look through the glass inside a restaurant and you see your friends there. Some of the light's being reflected so you can see other people on the sidewalk. And a lot of the light is passing through the glass so you can wave at your friends who are sitting in the restaurant. All right. That's what I mean by this reflected versus refracted ray. Now, what is the refracted ray? Well, once again, follow the incident ray. It comes in at some angle, and if there was nothing in its path, if nothing was there, the light would just continually traveling, following the yellow dots. But because there is something in the way, some transparent medium, the light bends in response. A good analogy to try and describe this is to talk about how fast the light is moving. Try running in, say, a track field. Right? Try and go your fastest sprint. When there's nothing in your way, you're going to go very fast. You're going to do your fastest possible speed. Now try running as fast as you can inside a crowded hallway. All right, there's people there. You're going to bump into them. You inherently slow down. Well, the same thing's true for light. When the light is outside of material, it's going to be traveling at its fastest possible speed. But when it hits this prism, it must slow down. And a property of that slowdown causes it to bend or refract. Now, how much the light bends, how far it's going to go away and change its path, it's based off of the material's index of refraction. So the index of refraction of this acrylic material here is different from the index of refraction of air. It's different from the index of refraction of water or diamonds or you name it. They're all going to have different indexes of refractions. And that's a material property. Going back to my runner analogy, think of the index of refraction of running in an open field versus a crowded hallway. The more things that are in the path, the greater your index of refraction. To see refraction in action, we're doing a slightly different setup. Here I've got the laser beam going straight up. You can just barely see it on the screen. Right? So the laser beam's coming straight up right now. And what I'm going to do is introduce a refracting material. I've got a nice prism here. It's a triangular prism. And I'm going to let that laser light that's going straight up refract through the prism. Let's go ahead and introduce it. And let's add some smoke so you actually can see the path. Right? The beam is going straight upwards, but it refracts in the medium and changes the path that it goes through. The path of a refracted beam is all based on the geometry, the angle that it hits the material at versus the angle that it refracts out. So we can exploit that geometry and create two of our most basic types of lenses. And they'll be converging and diverging lenses. Our converging lens has this kind of convex shape. Right? It vexes out, so these are also known as convex lenses. And the optical property here is that if I was to shoot a ray in nice and parallel, they will enter this lens, refract, and all the rays coming in nice and parallel will be focus. They'll pass through a focal point defined by this focal length. Well, instead of focusing the rays, we could also diverge the rays. So instead of having a convex geometry, I could go to a concave. Think of it as caving inwards. And this is our example of a diverging lens. So in this case, I'll send my rays in nice and parallel. And what they'll do is they'll enter this diverging lens and refract away. They will diverge away from each other. Also known as having a negative focal length, because the outgoing rays, these guys here, are on the opposite side of where they would focus if we could trace those rays backwards. Now let's actually look at these lenses in actual action. On the left will be a converging lens, on the right a diverging lens. Now to make all this visible, I'm going to kill my light and switch to a nice laser that I have mounted on this chalkboard. So there's my laser, and I'm first going to introduce my converging lens. And we just slide it up into the path of the beam. Where it hits on the lens will determine how much the beam will refract versus going right through and bending down. And as I slide the lens up, the trajectory of that refracted ray will change. Now, I'm going to shoot in a bunch of parallel rays. Every single one of these guys is coming in nice and parallel to each other. And I'm just going to put this converging lens right smack on top of that, and boom, there's the focus. All the rays are coming in nice and parallel, and they, bam, hit a focal point. These rays are being converged together. Now I'm going to try this again with the diverging lens. So let me slide this in, path of a single beam. Right. Seems similar. So let's bring in all the rays again. And I'll call this a diverging lens because these rays diverge. They come in nice and parallel and then leave at different trajectories. Hence why we call this a diverging lens. The paths diverge away from this lens. Other terms you'll hear associated with it are things like a negative focal length. Now, one last thing that'll matter for us. We won't do any examples of this. I just want to show you how do you make a telescope. You do what's called a compound lens. You combine different types of lenses. Look at this ray. I've taken what was 5 beams here, 5 beams, and I've split them up. Now say you're building an experiment, you're building a device, and you want to focus on these 3 rays. You don't care about the exterior ones. You want to kill those off, but you really need to focus on those interior ones. So make a 2-lens system. You'll have your rays come into the diverging lens to split up the rays. And now I'm going to put the converging lens, and I'm going to refocus the ones that I care about. So I've had this system that splits up all 5 and leaves me with just the 3 that I want to study. So this is your introductory example of a compound lens setup. And by combining our lenses in ways like this, we can create whatever kind of optical device that we want or need. One subtle nuance of these refracting properties through prisms and lenses is that the amount the rays refract actually depends on the color. It turns out that the blue and the violet rays, they'll bend slightly more than the red ways. And you'll see this in this prime example of sending in your nice white light source, and when it refracts out, you get the color dispersion, the rainbow. So by dispersion, we mean that there is this difference of bends through the medium, and that is a property of the medium itself and the wavelength of light going through it. Different wavelengths will correspondingly have different index or fractions in the material, and their refracted rays will bend out, refract at different angles. So you get that dispersion property, this splitting of the colors. And this is all fine and great if you want to study the individual colors. You want to do a spectral analysis. But if you're trying to take a picture, well, you need the white light source. You need the light as it came into you. So when you're trying to take pictures of images through your lenses, you have to fight this problem of chromatic aberration. We're breaking up the colors. A more schematic representation of this. Think of your white light source coming in. What's the white light? Well, it's all these different colors stacked on top of each other. Now, in this picture, they'll enter our converging lens, and the red versus the blues will bend different amounts. So they'll have different focal lengths. Here's red's focal length, green's focal length, blue's focal length. Well, as an observer, now it's really hard. I have these colors being distributed unevenly amongst the spectrum, and it's harder for me to resolve the image. Well, we do have a lot of tricks we can do. One example is to modify the geometry of our lens. Here in this example, we'd call this an achromatic doublet. What you're trying to do is have a converging lens here, sandwiched on top of something with just a flat edge. And what you're doing is you are mitigating how bad that dispersion is. Here, let's zoom in. Here's the bad. Here's the bad dispersion. And now let's zoom in again on the fix. And so by using your compound lens setup, you're making it better. You are getting a cleaner image. There's less dispersion. And that's just doing a compound setup again, trying to manipulate the properties of these refracted rays.